Today, we will talk a little bit more about ICP, its variants. So ICP has been introduced by 1992, a long time ago. And after that, there are lots of variants. So people try to use a better way, same idea, but better data association or better point filters, etc., in order to make the ICP even more effective or efficient. Today, we will talk about iterative closest points. We will call it ICP. This method was first introduced in 1992. That's 25 years ago. And it has been used in very different areas, especially in computer vision and robotics. Let's take a look at the formal problem formulation. If we got the right rotation and translation, essentially the transformation, right? And then you could fit from the left-hand side to the right-hand side. Okay, so let's take a look at the problem formulation. You have two corresponding point sets, X and P over here. And there are a few points here, actually n points, and you want to compute the translation T and the rotation R so that it will minimize the error. We already mentioned about many of the concepts. In many real-world applications, you may say, maybe in the first frame, you may have 2,000 data points. And in the second one, you have 2,300. Right? So you will see that this problem formulation is probably not exactly true because this is n, right? And this is also n. And over here, corresponding point sets. That means that for each point in your first data set, you got corresponding point in the second one. This problem formulation assumes that you already know the correspondence or the data association among the data points. So here comes the question, do you know the correspondence here? From the left-hand side, actually it's possible to calculate the rotation and translation very quickly because you know the correspondence. Actually, what ICP want to solve is not that easy. So if you know the correspondence, I could quickly brief you what you actually need to compute. So this is probably even in your linear algebra class already. So you find the point pairs, you compute the centroid, and you build a correlation matrix, and you estimate the rotation matrix R using SVD. So we already say many things about the linear algebra. You will get this shortly. But the ICP really want to solve is not that easy. In many real-world applications, from one scan to the second scan, you don't really know the correspondence. And the problem would be how to find the correspondence. But first things first, let's suppose we have already know the correspondence. So here is one example. And here is a data set A. You want to figure out rotation and translation so that the data set A could become data set B. There are just a few steps. You could calculate the rotation and translation. So the first step, you calculate the centroid of each data set. So that means you try to centralize or standardize it so that it could become a diagram like this. And the second thing, to calculate the H, which is the covariance matrix. And then you could use SVD. Actually, I have a paper using SVD to do some decomposition. The basic idea is that you want to find the least redundant element in the matrix. Yeah, so there are also many applications for SVD. And here, actually, it's kind of like a magic, right? But the rotation matrix, you could find it by V times U transpose. It's actually about do the rotation and then do some scaling over here. So this is actually the simple case. We don't really get into ICP yet, but this is something we need to know. Suppose we know the correspondence. So here we want to really get started to talk about ICP, and this is the usual case, ICP with unknown data association. And the main component, the first one is that you have two data sets. Usually people call it the model and target. So in our previous slide, the model, the target is the destination. We want to rotate and translate the original model one. Okay, and the first component is that how are we going to select the points? Okay, so here are two questions. Can we select important points? Okay, and the second one is can we speed it up? What's the pre-processing overhead? Depending on your scale of your data points. If the pre-processing takes too much time, too much overhead, it may or may not be worthy of doing this selection. But typically, doing the selection is a common practice. And the second thing is that how to search for potential associations, which means that in the model data set, suppose you have maybe 1,000 or maybe 2,000 data points, just like what Michael mentioned. And for each one, you want to search for a potential association on the target data set. And how are we going to do that? And three, we actually in the first frame and to the second frame, maybe some point doesn't exist anymore. Suppose your robot turned and could not see some of the data points in the previous frame, right? And also, there might be some outliers in your data set. And how are we going to identify those outliers or some mismatches? Okay, so keep in mind that we will talk about the main components for ICP in different steps. So can you see the white points and the blue points? So you could see that there are two sets of data points, and then the ICP is trying to do something about selecting association for the points, and also maybe do some filtering first, and later on do some outlier rejection. Since ICP was first introduced, there are lots of variants. You can think that the next 25 years until now, this is an important method, and people try to figure out better way to address the main components there. It's around 400 variants. And there is even statistics, like there is a paper try to review all those variants. And actually 400 is kind of amazing. I mean, there are lots of papers built on top of the original ICP concept, right? Okay, so suppose now you have invent something really cool and it could solve lots of problems. And if people use your method and or build on top of your method, then that will become very influential. I think this is a very nice paper published in Autonomous Robots in 2013. And they also have an open source library called Lib point matches. Okay, so let's get back to the three main components for those ICP. So essentially, those 400 variants are trying to improve the entire ICP in some way. Okay, and the first one is about how to select the important data points. Okay, and the second one is about how to find the association from one data set to the target. Okay, again, finally, that's reject some data pairs. And you could see diagram over here. Here is the reading. Reading is actually, people also call it a model, and the reference. And you could see that in the first stage in the pipeline, you could see some data filters. And next, you see some component called matcher. So the matcher is about the data association. And the next block called the outlier filter. Okay, so those are the main components for the ICP variant. The diagram here is from Thomas' robot paper 2013. Maybe we could have another brainstorm. Suppose we are younger, like 25 years ago, like we were have a time machine and ship the entire class. We just saw the original ICP in 1992. You could figure out some way to do some data filtering or some selection so that your entire ICP, the pipeline, could perform better. For example, if you have a 3D scan over here, this is probably somewhere outdoor, right? And then the original 3D scan has about 200,000 points. And you could imagine that 200K points, you want to find the association for each one. That will be kind of time consuming, lots of computation going on. But if you could extract some features, you could just keep about 5K points. That would be like 40 times fewer. So you could see that some of the feature points has been extracted from the original 200K. Okay, so this is one thing to do the selection, and it could be based on feature. Color is actually one of them, if you have that information. For example, Velodyne, then you won't be able to get the color. Yeah, but if you use a stereo camera or the different sensor, it may give you some different information. But for example, for 3D scan, so typically some corners will be important features. If you calculate the surface normal, and it will be kind of distinct. There are some other ways to select the points. For example, just use some uniform subsampling, and you could see it from the bottom left. So you just suppose your area is like this big, and they are pretty much the same. For example, a wall or a floor. Okay, and it doesn't really make sense that you just keep every single point on the wall, right? Because there are not much difference there. Okay, so in that case, maybe uniform subsampling will be useful and will greatly reduce the number of points. Okay, and you could see the next method called normal space sampling. And you could see the curve over there in the middle. It's actually kind of distinct area for the data set. If you just use a uniform sampling, you may miss it, right? So in that case, the normal space sampling actually also consider the surface normal and will get a few more points for this area with higher curvature, okay? And the next one is the feature. And there are also many good implementations in PCL already. Yeah, if you figure out maybe something more, and maybe you could write another paper, another ICP variants. Okay, and the second main component for ICP is the data association. And there are also several ways to do it. For example, the first one is actually the original ICP. You just try to find the closest point as the bottom left. And the second one is called normal shooting. This is the model data set, and here is one of the points, and you just calculate the surface normal and see the normal can reach which point on the target data set. The next one is called projection. So here is some viewpoint, and this is your model data set, and you will see like what this direction can reach on this target data set. For each method, there are actually some like pros and cons, although hold that thought. And the second important thing we want to know is that there are also some methods called closest compatible points. And it's kind of like a little bit similar to feature-based method. For example, based on the normals or based on the colors, etc. So you will not just blindly or randomly find some point. Okay, so this is another way to select another pair over here. But the simplest one, straightforward, will be just the closest point, Euclidean distance. And people also try to use different ways to find the points. For example, for closest point, it could be just like point to point, or you could also consider it as a point to plane. For example, if you have an object, then that would maybe a surface over here, and you could actually compute the point to that surface and get the shortest distance, the closest point between two data sets. And actually, the point to plane method is typically working better compared to point, except, for example, some unstructured environments. And we will talk about that later. So essentially, you have a pipeline of ICP, and you put different like a method or configurations among those key components. And some of them are maybe sensitive to the data. And some of them could perform better maybe in indoor, and some of them may be better for outdoor. Searching the points in 3D is the most computation expensive part for the algorithm. That's especially important in robotics because you want your robot or even run something on Pi 2, for example, then you definitely want a very efficient algorithm there. One way to speed up the search, we want to find the closest point among two data sets. And this is one way to speed up. And actually, the typical way to speed up, which is the KD tree. If you guys play with the PCL, and this is a very important data structure, and the idea is like this. Again, let's use a toy example first. And suppose you have a few points in the space here, and you want to build a tree so that it's the KD is D is for dimensional, so k-dimensional tree. You could actually see it from the left-hand side. It will try to split the points starting from here. And you got the first point, 51, 75 over here. And typically, you cut this first so that you will kind of evenly get your points in different dimensions. Okay, so this will be your root. Now you want to cut it horizontally. So you got the second one, this guy and this guy. Okay, so that you see that this is a 2540, which is that one. Okay, and 7070, which is this one. And you cut it horizontally so that in each area, you kind of get some points over there. And now maybe we could further cut it somehow. Let's maybe cut it vertically again. So usually the computation will alternate vertically and horizontally. Okay, and the next one, which is this. Again, you cut it here, and you have a branch over here. To construct the KD tree, just like what we mentioned, you have x, y, and xy. And the tree is always a binary tree. And the next step is that's really what ICP want to do, try to find k nearest neighbors, well, k could be 1 if you just want to find the closest point there. Okay, so you could actually do the search down. So for example, over here, if you want to find a point with minimum x value, you could try to get to this point, right? And you will ignore this part for now. And further down, over here, when you see like 35 is greater than 10, you probably could just ignore the rest. Okay, not really. This slide, actually this will take the entire course to explain how to construct, how to insert something in the KD tree. And then you will have another course to explain how to find KNN in this KD tree. I hope that you will still get the basic concept of KD tree, how to build a KD tree and how much it could speed up. Okay, so before we use the KD tree, what's the original complexity of this problem? I mean, if we do not use KD tree and you want to find the corresponding points, for example, you want to find the closest point. So essentially, the big O notation will be n squared. So you could reduce the complexity from n squared to actually n log. Actually, that's a big improvement for efficiency. If you want to construct the KD tree, that's kind of another overhead for you. Here's another thing. In practice, typically, if you, depending on the number of points in your data set, sometimes if you have an unorganized point cloud, and you could actually build the KD tree, right? The computation speed will be still kind of expensive if you run something on embedded computer. But if you have an organized point cloud, for example, you have a Connect sensor, or you have a stereo camera, and you have the RGB and the range here. More importantly, actually you don't need RGB. Suppose you have this. If you want to find the closest point, typically you just need to search area within a small patch in this depth map. Because for each one, you already know what's the points over there. And you could even use, for example, integral image to compute the gradient in the depth image. So this is just that you know that although KD tree is a desire, could highly reduce the computation, but building a KD tree itself sometimes become maybe expensive in the embedded platform. Last main component is to reject some of the outlier point pairs. One popular method is called trimmed ICP, which remove the higher distance quantiles just of all pair points. Here, we just mentioned that the algorithm may be sensitive to different data sets, maybe indoor, outdoor, structured, unstructured. Here is one example, a case study. On our right-hand side is the robot that can actually climb. And then the data set is indoor environment, but with 7 floors. And you could see that the following here, they are the ICP pipelines, and there are some considerations over here. Okay, so for data filtering, I hope you guys can still see the description here. Okay, so for the filtering, this one use surface normal and also use some random subsampling and keep 50%. Okay, so all of those, we just mentioned that. Okay, and for data association, it uses the KD tree with 0.5 meter max distance. So if the distance is longer than 0.5, we will just discard that point. Suppose the point, you could not find any close point between two data sets. And this one, for outliers, it will keep 95% closest points. Okay, and also try to remove the normals that are more than 45 degrees. Okay, and it uses the point to plant as the error minimization. Finally, there is another checking called transformation checking, and the minimum error below 1 cm and 0.001 radius will be excluded. And the iteration counts reach 30. Okay, so you could see that for this case study, you could use those settings for your ICP and test that on a particular data set. And you may actually get different results among different data sets. So this is another paper in IJRR 2012. And the data set includes some environment, like structured environments, as well as some unstructured ones. Or the data set with more dynamics objects in the data set or in the temporal domain. So even that the season changes. Okay, so very fast to very slow.